Good evening. I hope you're doing well. So I promised you that I would prove these properties of logarithms to you just for those that are curious. The first one, logarithm of b power 1, that's always equal to 0 because, like I told you in the last video, you're asking yourself, to what power do I raise b to get 1? To what power do I raise b to get an answer of 1? Since you know that 1 is the same thing as b to the power 0, and the bases being the same, x is equal to 0. So that means that the power to which you raise b to get 1 is 0. So the logarithm of 1 is always going to be 0. Even natural log of 1 is equal to 0. This one, logarithm of b to the power b, that's always equal to 1, because again you're asking yourself, to what power do I raise b? To what power do I raise b to get b? Well, that power is 1, so x is equal to 1. Alright, let's look at the product rule of logarithms. We said that if you have a product of m and n, the logarithm of a product of m and n, then that's just equal to the logarithm of m plus the logarithm of n. Why is that? Let's start off with two things here. Let's say that b to the power x is equal to y, right? Oh no, sorry, is equal to m, and then b to the power y is equal to n, right? We have those two things. If that's the case, that means that logarithm base b to the power m is equal to x. That's what that means. And this means that logarithm basis b n is equal to y. This goes back to the same thing as that if I use that cycle. It goes back to the same thing. So it's the same thing. Now, again, starting with this, if b to the power x is m and b to the power y is n, remember my product was mn, so I'm trying to recreate this product. And that's going to happen if I multiply these two. So if I multiply b to the power x times b to the power y, then on this side I'm going to have m times n, because I'm multiplying b to the power x, b to the power y, that's equal to the same thing as m times n. This is the same base, and according to the laws of indices, if the base is the same and I'm multiplying, then I can add the powers. So that's b to the power x plus y is equal to m times n, which is just mn. Alright, next, I can, if I want to have this x plus y as something on its own, I need to get rid of the b. The only way I can get rid of the b is if I introduce a logarithm to the base b. If I introduce a logarithm to the base b, just use a black here. If I introduce logarithm to the base b on both sides, and this is a valid mathematical symbol, kind of like dividing by the same thing both sides, or multiplying by the same thing both sides, or squaring both sides. This is also another valid mathematical expression or operation. I can introduce logarithm to the base b on both sides, and remember, every time I have this scenario b and b in the same place, that's going to cancel out, and I'll just be left with x plus y, which I have down here, is equal to, x plus y is equal to logarithm base b m times n, right? So I have logarithm base b m times n is equal to x plus y. But remember that my x alone is the logarithm of m to the base b. So instead of having logarithm base b m times n is equal to x plus y, I'm going to substitute for x and y. And my x alone is logarithm of b to the power m. Logarithm of b to the power m. And the logarithm of, y alone, y is equal to logarithm of n to the base b. So that's my proof that every time I'm multiplying logarithms, right? Every time I'm multiplying numbers, that's the same thing as adding the logarithms of those numbers. That is the proof of the product to addition property of logarithms. Quotient, same idea. I'm starting with the same idea, but instead of multiplying them, I will divide them. So it's the same exact idea. I will start with b to the power x is equal to m, and b to the power y is equal to n, And as logarithms, this is the same thing as x equals logarithm of b to the m, and y is equal to logarithm base b per n, right? So then I'm going to use these two values, and instead of multiplying them, since I want to get a quotient, I will divide them. I'll divide b to the power x divided by b to the power y, and that's going to be equal to m divided by n. So m divided by n. What I can do at this stage is I can use the laws of indices, because since these bases are the same, the laws of indices say that if you're dividing, you subtract the powers. So this will be b to the power x minus y is equal to m divided by n. Now at this stage, I can introduce a logarithm. If I want to get rid of the b, from here I can introduce a logarithm to the base b on both sides. Logarithm to the base b. Like I said, this is a valid mathematical operation. If I introduce that logarithm, we'll kill this. Then I'll be left with x minus y is equal to logarithm base b m divided by n. So just to write it, logarithm base b m divided by n is equal to x minus y. Again, remember that my x alone, x is the same as this x is the same as logarithm of m to the base b, right? So I have log m over n base b is equal to x. Instead of x, I'm going to put logarithm of m to the base b, and instead of y, I'll put logarithm of n to the base b. So I've proved the quotient to subtraction property of logarithm. If you're dividing two numbers, then just subtract their logarithms. The power rule for logarithms states that if you have logarithm base b m to the power n, then the power drops to the front. So let's see how that happens. Starting with the same idea, if I have b to the power x is equal to, say, m, right? B to the power x is equal to m. That means that if I have b to the power x is equal to m, which is the same thing, and remember this, I can write it as a logarithm. That will be logarithm base b power m is equal to x, or x equals logarithm of m base b. So I technically have m is equal to b to the power x. If I introduce another power, if I raise this whole equation to the same power, say k, if I raise this to the power k, and I raise this also to the same power k, I have not changed the meaning, right? I've not changed the meaning of this equation. So I have m to the power k is equal to b to the power kx, right? Now I'm going to introduce logarithm to the base b on both sides. Introduce logarithm to the base b. Logarithm to the base b, logarithm to the base b. This side I have m to the power k, and this side I have b to the power kx. Alright, so logarithm base b m to the power k is equal to k times x times, remember logarithm of b, base b is just 1. So on the right side I'll just have k times x, and then on the other side I'll have logarithm of base b m to the power k, right? So kx is what I have on the right hand side, but remember my x is just the same as logarithm of m to the base b. So I'll substitute for that. I have logarithm of b m to the k is equal to k times x, but remember x is just logarithm of b to the m. So that tells you that every time you have a power on the power of a logarithm, every time you have a power on this power of a logarithm, then just or drop that power to the infront, to the front. Drop that power to the front, and then it's just that power times the logarithm. So if you had logarithm of base 2, 43, power 12, and it's just the same thing as 12 times logarithm 43 base 2. Alright, change of logarithm, change of base formula for logarithms. This is the last one. How, if I have a logarithm of m to the base b, I can write it as, I can introduce any base that I want and write it as logarithm of m to that base divided by logarithm of b to that base. How does this happen? So again, starting with the same idea, if I have b to the power x is equal to m, right? To the power x is equal to m. Remember, this is the same thing as logarithm of m to the base b is equal to x, because the cycle works. So if I have b to the power x is equal to m, that's where I'm going to start. Sorry about that. I can introduce a logarithm to any base that I like, right? If I want to introduce a logarithm to base p, I can do that because I choose p. Logarithm to the base p, b to the power x is equal to logarithm to the base p, m. All right. From the what? From the this thing that we just put, the power rule of logarithms, we know that if you have a power on top of a logarithm, that power drops to the front. So that's the idea I'm going to use here. Since I have this power on top of the logarithm, x will just drop to the front of the logarithm. So it'll be x logarithm of b base p is equal to logarithm of m base p, right? So if I want to isolate the x, I'll divide both sides by logarithm of b base p, divide both sides by logarithm of b base p. So this cancels out, and I'm left with x is equal to logarithm p m divided by logarithm base p to the power b. However, remember that x is the same thing as logarithm of m to the base b. So since x is that, I'll substitute for x and I'll end up with logarithm of b, base b power m is equal to the same thing as logarithm of m base p divided by logarithm of b base p. And I urge you to try this out on your calculator. Just try random things, like if in your mind you're thinking logarithm of 16 power 48, right? Try on your calculator to check, is this the same thing as logarithm of 48 base 10 divided by logarithm of 16 base 10, right? Is it the same thing as logarithm of 48 logarithm? Because you can introduce any base that you want. And this skill is going to be useful when you're asked to compute various logarithms without using a calculator. Some of you are wondering, why am I having to do these things without using a calculator? And you are right. Practically, you may not need to use these ideas at all, because these days you have machines that can do the computation for you. But because you know this, it can open doors to different pathways in your thinking and in your manipulation of equations, work, problem solving. Yeah. So, and at this stage, you really have to, this is the stage where your brain gets to expand in terms of your ability to solve problems like this. So just relish the challenge. Yeah, that's it.